So welcome back. And before we get started with a new topic, I just wanted to quickly go through what we did before the winter break. And what we have done is to cover what you might call pre-2000 methods for machine learning. And we went through some topics which are also more modern, like the resampling techniques and also the discussion of gradient methods and the way we actually implement an optimal way of updating the learning rate. And this is going to turn very useful when we now move into deep learning methods. So everything which we went through before the break are in a way older methods. You can think of this as a kind of not exactly low level machine learning, but it exposes many of the basic principles. But at the same time, these are methods which have been really replaced by deep learning methods. And nowadays, if you're dealing with scientific applications, you will often find things like physics-driven machine learning. You will find topics like dimensionality reduction methods and so on, which are really at the frontier of what you might call data-driven science and engineering. Now, we ended with a discussion of the optimization methods. What I've done is to also add some slides on support vector machines, which we didn't cover before the break, but I just put the slides here. And you can take a look at them if you want to. So support vector machines have been also widely used, and I'd say till 2008 and 2009, before we jumped into deep learning methods, then these were very, very popular methods for both classification, mainly classification first, but also for regression type of problems. So the topic now, which will also gear up to project number 2, is essentially to get started with deep learning methods. And that means that we are going to start with neural networks, which in general are seen as dense methods in the sense that we are going to deal with all the data which we have. So we are going to essentially rewrite everything in terms of matrix and matrix vector multiplications. And these matrices are going to be dense, and they will contain the parameters of the theory. And when we've done that, we are going to dive into building a neural network code and how we can actually set it up. We are going to look then at a popular library which was released by Google, which is called TensorFlow, which also has some very nice APIs like Keras. And then we are going to solve differential equations with that. And then we move on to convolutional neural networks. And then at the end, we stop with recurrent neural networks. We may, if we have time, we may discuss autoencoders and also generative adversarial neural networks. This is a topic which we can bring up at the end here. But I'm going to spend a little bit of the time on first on the whiteboard here, and just write down some of the basic things which we are going to need. And the aim today is to get started with this important algorithm, which is called the backpropagation algorithm. Now, the one thing I wanted to say is that the backpropagation algorithm is tightly linked with perhaps one of the better algorithms which we have, which is called automatic differentiation. We mentioned that before the break when we looked at the stochastic gradient methods and the different gradient methods. So this automatic differentiation is a algorithm which is based on repeated application of the chain rules and also usage of functions like cosine, sines, and exponentials, which allows you to calculate derivatives to numerical precision. And it's way better than any of the standard algorithms, like those based on finite difference, or if you use symbolic packages like Mathematica or SymPy, which often tend to give you very long and wieldy expressions to implement numerically. So automatic differentiation has two types of modes. One, which is called the forward mode, which we're going to discuss. And same, the other mode is called reverse mode. And reverse mode in automatic differentiation is actually the same as the back propagation algorithm. This is something which is under-communicated in the machine learning community. So when we look at the back propagation algorithm, we need also to discuss what is behind automatic differentiation. And as I mentioned before the break, automatic differentiation is one of these algorithms which really saves the day for us, because you can calculate, if you have complicated functions, you can really calculate derivatives of these functions without having to go through all the hassle of paper and pencil work where you write down the derivatives and then write the codes for them. So this is something which we strongly recommend when you are writing your own codes. So let me now switch back to the whiteboard, and then we're going to stay there for some time. Can you all see the whiteboard properly? Is it all okay?
Yes. Yes, yes.
Okay, goody. So let's try to get started, and I'm going to give a kind of list of items which we will start to cover. So when we now look at deep learning, the first type of method which we are going to look at is a neural network. And I'm going to shorten that one just to NN. We are going to look at an explicit algorithm, which is called a feedforward neural network. So you will often see that one shortened to an FFNN. Sometimes you will also see this abbreviated to a multi-layer perceptron model, because this is very much inspired from neuroscience. And the perceptron model was actually a model which was introduced to mimic the behavior of a neuron. So I will interchangeably use words like neurons, nodes, or units to indicate the same quantity. But if we now look at the important components, whether we are doing feed-forward neural networks, or we are looking at convolutional neural networks, or recurrent neural networks, or any of these methods, you will also notice that it's going to be useful to have a graphical image of what is going to take place. But let's now look at the important ingredients. So one of the important ingredients is the universal approximation theorem, which we will come back to later. We are not going to prove it, but we're going to state it. This theorem plays a central role here. And the theorem states that you can approximate to a given error a continuous function if you have at least one hidden layer in a neural network. And that's an extremely powerful theorem. And we are going to state it mathematically just a little bit later. But now I just wanted to give you the what are the basic ingredients. But the universal approximation theorem, if you think back of what you've seen when you do a polynomial approximation, you have something which is called Weierstrass theorem, which tells you what the kind of error you have when you approximate a function with a polynomial expression. You have similar error estimates when you set up a Fourier transform to approximate, let's say, a periodic function, etc., etc. So in mathematics, there are several of these theorems which tells you how large an error you make when you perform a specific mathematical representation of a function. So the universal approximation theorem states that you can approximate a continuous real function to a given precision with at least one hidden layer. It doesn't say anything about the number of nodes you have, the number of layers you have, and the kind of architecture. So one thing which becomes important for us then, when we are using the universal approximation theorem, is the architecture. And that defines, in a way, what is our model. So if you think back to what we discussed in linear regression, we made a model of a function, and the simplest possible model we could make is oftenly a polynomial approximation. So the examples which I used in the lectures before the break were when we're looking at regression, was to approximate a function with a given polynomial. Now, in this specific case, what we need now is to decide. So what defines our model now is the number of hidden layers. And we are going to go through these quantities and discuss what they mean. The number of hidden layers and what we are going to call nodes, and the number of nodes and neurons or units in the different hidden layers. So these become parameters in the theory here. Like you would have a polynomial approximation in terms of a given degree of the polynomial as your model. So you can think of the architecture here as the model which we are going to use to represent the data set which we have. Now, this is going to include also things like activation functions, which I'm going to discuss a little bit more in detail later. And I'm going to generically call these activation functions for a function sigma, and that takes in a specific argument z. So the activation functions become part of the model. Now, when we move on to convolutional neural layers and recurrent neural networks, we are going to meet additional ways of setting up the architecture. So when we do a convolutional neural network, just to anticipate what is going to come, a normal feed-forward neural network is normally called a dense matrix operation system, in the sense that we are going to deal with the full matrices, and we are not going to try to reduce the dimensionality. Now, a convolutional neural network, which has had a huge success when it comes to recognition of images, is a network where we try to reduce the dimensionality of the problem through the mathematical process of convolution. So that's a way to add further model features. But if we now look at the standard neural network, the basic one, which we're going to encounter, this now contains hidden layers and a given number of nodes, and it's going to contain activation functions as the setup for our model. Then, when we have decided on the model, and everything which you see here brings in different parameters, we need to set up the type of cost function or loss function, as we have interchangeably called them, loss function, and the optimization method and optimization algorithm. So the topics which we then would need would clearly be the type of loss function or cost function. We need to describe what kind of regularization we are going to deal with, whether we have an L2 or an L1 norm type of regularization. Then we need also to look at the different gradient descent methods. So I'm just going to put this in a common container. And typically then what you need to discuss is whether you want to do a stochastic gradient descent, number of batches and epochs you want to have, and all the parameters which follow the discussion of a typical gradient descent method, which were topics which we discussed a little bit before the break. So what I'm going to do now is to go back to the simplest possible case which we could have, and we're going to represent graphically a linear model which is the same as what we did when we did linear regression. So let us look at now a example with linear regression. So where we assume now that there is a linear dependence on the unknown parameters. So it doesn't need to be linear regression only. It could also be a classification problem. And then we ended up with what we call logistic regression before, as we discussed before the break. So what we could think of now is to look at a simple system where we consider two inputs. And we are going to call these inputs x1 and x2. That means that we would have a vector x, which now is given by, so this is x transpose, which is given by x1 and x2 here. And one of the things which we are going to use repeatedly is now a graphical representation of the data here and the models which we are setting up. So we are going to now have a node. So we are going to call this for a node or neuron. The model which I'm setting up now is called the simple perceptron model, which is very much was inspired by research in neuroscience. And this node here, which we now are going to represent mathematically by this activation function. So this is our activation function. Now we have an input x1 and x2. This input is transformed into this variable z, and then it produces an output. So this is our input. We can now think of this as an input layer. I'm just bringing up the different names and the types of variables which we're going to deal with. So we have defined an input layer. We now have this node, which is where this input is fed in. And then this activation function can then produce an output depending on the type of operations we want to have. So you could think of this activation function producing a 1 or 0. If you're thinking of something like a gate in electronics, you could assume now that if the input here gives you a voltage, when it has gone through this function sigma z, it gives a voltage which is 1 or larger, or less than that one. If it's larger than a certain threshold, it produces a bit 1. If it's below a certain threshold, it produces a bit 0. So we were just going to call what you see here in a generic way for the output. And I'm also going to change a little bit the names of the variables. So I'm going to call this output y. And this is the one which is now produced by our model. So what you see here is just a way to represent our model in a graphical way. Now, in here, we would have some cost function or loss function. Cost loss function. And I just write this with a C. And this y here, which is the output of the model, is now fed into the cost function. And then this is compared with what we are going to call for the targets. And the target is the variable which we, or the data set which we want to reproduce. So we have some inputs, and then we have the outputs which are produced by the model. And these are then compared with the targets which we want to reproduce. And then we can go back and forth here and find an optimal way of representing the model which reproduces the targets. So in here, we are now going to have an unknown quantity W1, which we can call for a weight. So these are the unknown parameters. It's just like what we had previously with the parameters beta. And this model, which we are going to have now, is going to mimic the simplest possible case we had when we looked at a polynomial approximation. At the same time here, there is going to be a new parameter, which I'm going to call for a B, which is normally called for a bias. And this parameter is normally used in order to avoid, during the training of a neural network, that these W1s and W2s become equal to 0. And so the bias in the simpler case, when we do linear regression, that is something which we can interpret as the intercept of a polynomial fit for a given function. So what we have here is then something which we are going to call for an input or input layer, and then we have an output layer. And finally, we feed that one in to the cost function here, and where we compare with the results we want to reproduce. Now, this simple model here is something which we now can rewrite in terms of the different variables. So this function z, which inputs to sigma, is now going to be given by an x1 times an w1 plus an x2 times a w2 plus this variable b here. And now we could assume that this sigma z, so sigma z in the simplest possible case, is something which we can simply set up as this function x times w1 plus x2 times w2 plus b. So that the function sigma doesn't do anything but just accepting this value z. And this defines our output. We would write this in a more compact way. We would have a data set of t, y, and then clearly we want to produce this output y of I. So that means that what we are going to have more generically is this y of I is going to be given by this function sigma of x of I, and then we are going to rewrite this in a more compact way where we have theta as a collective container for the unknown parameters. And in our case, the simple case which we have here, we have a vector x of I. These are the input parameters transposed, multiplied with this w plus b, where w now plays the role of a vector which contains the unknown parameters w1 and w2 here. So the parameter theta is just a collective container for the unknown variables w and b. And you can think now, since we now just have x1 and x2, so for a specific input set I, then we have a component x1 and a component x2. And to that one, we want to associate these weights w1 and w2, and then we have a bias. So if you look back at what we have here, if we take this simple approach to the model, what you have here would not be nothing that the standard linear regression, which we have studied before, but now with the two variables x1 and x2, plus a value b, which now could function as the intercept. So let's take a look at a very simple case, which we now are going to study with the linear regression and logistic regression. And this case which we are going to look at is something which we call the OR gate, and you may have seen that before. And this specific gate is a famous gate in electronics. So what you would have now would be an input here. So you would send in variables x1 and x2, which can take the values 0 and 1. So this would be bits 0 and 1. This produces an output, y. And this output here, if we now look at this specific gate and we make a table, so we would have x1, x2, and let's now, instead of y here, just call this for t, because this is the target which this specific gate is producing. So we would now have, if we now make a table here, what we have, if we have x1 is 0 and x2 is 0, this gives 0. And since it's an OR gate, it's either x1 or x2, so this gives 1. And then we have 1, 0, and this gives 1. And then we have 1, 1, and 1 as output here. And I assume that you've seen this type of gates in electronics before. Now, this means that if we now look at the vector x, the way we have defined it, the vector x would now contain of four possibility. So I would have x1 being 0 and x2 being 0. I have x1 being 0 and x2 being 1. And then I have 1 and 0. And finally, I have 1 and 1. So this would be the set of the input variables which I have. And clearly then what it means is that my output t is now simply given by 0, 1, 1, and 1. So this is a pretty famous gate. Now, if you now look at what we have, if we want to make a plot here, so you could now think of plotting these quantities. So we plot x1 here on the x-axis and x2 on the y-axis. And we have only two values. So it's 0 and 1. And what we know then is that in case we have 0, 0, then 0 is the output. So I just mark it with 0 here. If we have 0 and 1, then the output is 1. So I'm marking that with a filled circle. And 1 and 1 here. Now, if you look at this figure here, you could now think of fitting a line which separates the two classes of outputs. So we have only two classes of outputs, either 0 and 1. So think of a line fitting. This would be the simplest way we could actually implement our linear regression case. Think of a line fit, where we now just want to find a line which separates the two cases. So we make a model where we have y, which we obviously want to be equal to t, where we just have x1 times w1 plus x2 plus w2 plus this b, which we call the bias, which is now going to play the role of the intercept. And this is nothing but this x transposed times w plus b. And now if we make such a fit of a line with these data sets, we could actually use linear regression, or we could use logistic regression, since we only have a discrete outputs here. But we could think now of fitting a line, and this line could look something like this. Suppose this is the fitted line after we have applied linear regression. And then what we could say is that if the value is now smaller than a specific value, then we give bit 0. If it's larger than a specific value, so if it's in this region here, we would have y equal to 1. And in this region here, we would have y equal to 0. Does that sound reasonable? So this is just a simple way by which we can get started with thinking of using what we have seen before. But what you're going to see now is that there is another gate, which is called the XOR gate, where this kind of approach is going to fail miserably. So let's look at the XOR gate. So the XOR gate has now the same inputs. So that means that when we are going to set up a model for linear regression, the design matrix is going to be exactly the same. But then we have outputs now. So let's just set up the table. So we would have a 0, 0, and then 0, and then 0, 1, 1, 1, 0, 1, and then 0, 0, 0. So that's the XOR gate. Now, if we now plot this in the same way as we did for the OR gate, so let's look at a simple plot here. So we have 0, this is x1 again, and we have 1, and we have 0 and 1 here, and this is x2. Now what we have, if we have 0, 0, then we get 0. I use that an open circle here, so this to indicate that that's 0. And if I have 1, 1, sorry, this was wrong. I actually, let me rewrite it. This is 1 and 1, and that gives 0. So if I now have 1, 1, I also get 0. And then if I have 1, 0 or 0, 1, then I get 1. Now what you see immediately here, if I want to fit a line in order to separate the two faces, this is something which is not possible because I could fit one line which goes here, but then you see that I would misfit, I would not fit properly the value which I have here, because then I would have an intruder data point. I could think of fitting two lines, but actually here I would need to fit something like this, which would not be possible with a simple model which we have put up here. So we have a very simple activation. And this simple activation here says that we have a linear relationship between the unknown parameters and the inputs and the output. And this leads to a kind of more general result that if I'm setting up a neural network with just no hidden layers, so this would be an example of a neural network without a hidden layer, because we are just taking the inputs. There is no hidden layer. The inputs are manipulated through this function sigma z, which defines our model, and that produces an output. Now, you can show mathematically that this will not take into account the nonlinearity which is coming out of this model here, the XOR gate. Now, let's now look at this without knowing this kind of problem. Let's now simply assume that we want to use linear regression. And what we do then is that we, if we now look at the basics, we can now set up a design matrix. So suppose we want to use logistic regression or linear regression. We would now set up a design matrix based on the type of input which we have. So if you now think of the type of inputs, we would have a vector x, 0, 0, which is multiplied with the unknown variables, w1 and w2. And then we have a new unknown parameter, which is the bias. And this is going to be equal to our y, which we want to be equal to 0. So that's the first element. And then we have 0, 1, which we will multiply with w1 and w2 here, plus this b. And that's going to give us our output, which we want to be equal to 1. Or something which could allow us to make a decision if we have a line that if the value is given by something larger than a certain value, then we put it to 1. If it's below a certain value, we put it to 0. And then we have 1, 0 multiplied with w1 and w2 here, plus b. And this is given our model output y, which is equal to 1. This is what we want. So we would then have to set up a design matrix where we now can fit these unknown variables. Plus b equal to y equal to 1 here. So what we would have would be the unknown variables, which are now given by this quantity theta, that would contain b, the intercept, w1 and w2. And we know that these parameter theta, they are given by the design matrix multiplied with the itself inverse of xt and multiplied with a target t. So the design matrix in this case, if we now look carefully at what we have here, so you see now that the b's, they just come with a parameter 1. So that means that if we look at the design matrix, this would now, in this specific case, it would now contain the column for the intercept, if we want to use this intercept. And then we would have x1 and x2. So we would have 0 and 0, 0 and 1, 1, 0, and 1, 1 here. So this is the way the design matrix is going to look like. And we can actually calculate easily then the design matrix transpose times x. And we can also put up the design matrix inverse. So it's pretty easy to calculate that one. And if you do that, you will get 3 divided by 4, minus a half, minus a half, and this is minus a half. And then I have 1, 0, 0, 1, and then minus a half here. So that means the following, that we can find this parameter theta, the optimal ones, using plain standard linear regression. And this is going to be given by an intercept which is a half and 0, 0 for W1 and W2. Sorry, this is in case the, sorry, that was wrong. Let me just put that one back again. I was reading the wrong line. So this is 1 divided by 4 for the XOR gate. And then 1/2. So this is the OR gate. And it's easy to check that. And that gives us then a prediction, Y, which is equal, so Y transpose, which is equal to 1 divided by 4. I get 3 divided by 4, 3 divided by 4, and 5 divided by 4. The target which we want to reproduce is, in our case here, 0, 1, 1, 1. So what we could say now, if we look at this specific fit we made, if Y is larger than a half, then output Y is equal to 1, else we just put the output to 0. So that's the way we can now use this output to simply say that we have now fitted a line which gives us these values. And with that fitted line, we would say if it's above a specific value, we get 1. If it's below, we put it to 0. If I take the XOR gate, on the other hand, so the design matrix is the same all the time, then what we are going to get then is a parameter, an optimal parameter theta, which is now given by 1/2, 0, and 0. Now, what happens then is that I'm going to make a prediction here, which simply says that my Y of t is going to be equal to this design matrix multiplied with the optimal parameters. This is just a reminder of what we did with linear regression. And then we are going to get the values of 1/2, 1/2, 1/2, and 1/2. So that means that if I want to use linear regression, and logistic regression is going to give me basically the same type of results, this actually fails. So I cannot separate, because my target t is going to be equal to 0, 1, 1, 0. And you see now that since my prediction is the same value for all the outputs, that means that I cannot say that if it's less than a half, it should be 0. If it's larger than a half, it should be 1. So actually, using linear regression here, the way we have set it up fails miserably. So this also leads to a statement that this model, which we call the single perceptron model, or it's often called the simple perceptron model, the single perceptron model and if we look at this graphical representation, which we did up here, this is a model without a hidden layer. This is a model which actually now is able to reproduce problems which can be fit by a linear function or linear dependence, but it fails if we have a more complex result, where we do not have a clear linear dependence. So when I say a clear linear dependence, if you look at the XOR gate, we cannot define just one line which separates the two observations, classes of observations. In the OR gate, and you will also see that if you deal with an AND gate, in an OR gate, you could actually think of fitting just a line here, which separates the two phases or the two types of observations. So when we get something which does not have this clear linear behavior, then this simple perceptron model, which we have adopted, which essentially becomes the same as the classical linear regression or logistic regression. We see that this simple perceptron model, which has no hidden layers, and you can actually show mathematically that having hidden layers give you this non-linearity, no hidden layers. Fails in reproducing data which require a nonlinear approximation or description. So this is this simple example which we put up here is a example which is now used to simply decide what kind of approach we should use. So if we have a plain linear behavior, there is no need to actually go beyond a standard linear regression or even the simple perceptron model. But as soon as we have non-linearities in the data, which is perhaps the most common situation, then we need now to look at something which is more complicated. So if we now look at this case which we had till now, if we now introduce a hidden layer, then we would actually be able to reproduce this XOR gate as well. So let's now look at the first type of model which we could make. So we could start now by adding a hidden layer. And now we're going to make the model a little bit more complex. And adding this hidden layer introduces immediately a non-linearity. And that's the kind of complexity which we will need in order to describe this type of data sets, which we saw, for instance, with the XOR gate. So the way we're going to draw things graphically is as follows. So we're going to have an input layer, as before. And for this specific case, which we've been looking at, so if we just stick with the XOR gate, what we are going to have then, if we do the graphical setup, so we would have an X1 here. This is one node. We call these input nodes or input layers. So we have an input node 1 and an input node 2. Then we are going to have a hidden layer. So that's the next layer which we have. And we're going to draw it like this. And in this case, we are just going to have two nodes. So remember now that this is something which is going to define the architecture here. So we would have a node H1, and then we have a node H2 here. And then these hidden layers with a given input, they conspire to produce an output. So in this case, we have only one output. It was either 0 or 1. So what we would have then would just be one node. This produces an output Y, which then is compared with a target in the cost function here. So we have a T here, which is a target we want to reproduce, which feeds into the cost function. And then that is where we compare the model result, which now is defined by this network. And this is going to be a fully connected layer, which means that we have a node X1, which connects with the these two hidden nodes. And then we have a similar connection between the input node x2 and the different two nodes in which we have in the hidden layer. So there's going to be a parameter here, a W11. There's going to be a new parameter, W12. We will have a parameter W21 here and a parameter W22 here. So that means that we are going to feed in from the input layer. We're going to feed that into the hidden layer. This is manipulated by this function sigma of z. We are going to have, for each of these variables here, these hidden nodes, we are going to have a bias, B2 and B1. This is done in order to hinder that the training can stop at a given hidden layer in case the gradients become zero. This is a problem of vanishing gradients. We are coming back to that. And this now connects with the hidden layers, connect with the output layer, and where we finally produce the final values y. And this is also modulated by, and we're going to put labels on it. So this is a sigma h here. This has an h, and h. And here we have a W1, a new parameter, because the values which come from the hidden nodes are then fed into the output layer. So we're going to put this an O here to indicate that this is related to the output layer. And we have a new parameter here. And you can also have a bias here, which we can call, so we're going to put an H on top of this one, an H on top of here, and then we have a bias here, which is also a parameter. So you see now that if you start counting, before we take a break, we have 1, 2, 3, 4, 5, 6, 7, 8, and 9 parameters to optimize, and in order to find the best possible representation of the final results here. So this is the basic architecture which we now could use in order to try to see if we could be able to make a model for this XOR gate. This is as simple as possible. Now, the model itself is now defined by the architecture which we have chosen, the number of hidden layers, the number of nodes, and clearly this will also depend on the type of activation functions which we are dealing with. So in here, we also have an activation function, and we need to put labels now. We have an H, this is an output layer, and so we put an O on top of it to indicate that this is the output layer. But this is the basic structure of a neural network with just one hidden layer. Now, I went a little bit over time here, and I'm going to stop the recording and we can take a small break. Now, what I'm going to do now is to, based on this kind of simple model, which have just one hidden layer and two nodes, I'm going to try to make some generalizations based on that. What we would have now, if you look at the connection between the input layer and the output layer and the hidden layer, what we end up with then is something which we could express mathematically from the input to the hidden layer. We would then express to the hidden layer. This is something which we now could express mathematically in terms of a matrix W with the matrix elements represented by these nodes. So these are unknown parameters, and we multiply this with x1 and x2 here. And we can write this in a more compact way as a W, matrix W times the vector x. And this matrix W can obviously have different dimensionalities. Now, this result, which we have here, is now fed into these hidden nodes. So it means that the hidden nodes which we have, if we now look at this given hidden nodes, and we are having two hidden nodes, H1 and H2. And we are not going to put a label on top of them because we have only one hidden layer. And these hidden nodes, they produce an output. So this is the output from the hidden nodes. And this output is now given by this function, which we have defined upon as an activation function. So we call this a specific activation function. And that takes as input. So these h's are now given by this function sigma, where we put a superscript h. And that takes as input the variable x. It has this unknown parameters w, and represented by the matrix. And then it contains also these biases, which are the unknown parameters. So we are going to write this in terms of a vector b. So in this case, we had defined this as a b1 and b2. So this vector b is now given by these two terms, b1 for the hidden layer and b2 for the same hidden layer. So these are the unknown parameters, and we would often write this as a sigma for the hidden layer, and this contains x, and then we have the unknown parameters in this collective container theta. And this produces now an output from the hidden layer. So this h here, in our specific case, is now something which we need to define in terms of an activation function. So this h needs an activation function. And we are going to look at different types of functions. One of the things we want this function to be is a function which we can easily calculate the derivative of. We want it to be continuous. And there are many possibilities here. And you probably have heard about the sigmoid function. We are coming back to these different types of functions. But a simple one is something which is called the sigma of z. One of the simplest possible ones is called the rectified linear unit. Now, as I said in the previous lecture, if you look at the structure of a neural network, if we go scroll back a little bit and look at the more general features of a neural network, so we have what we call the architecture. And the architecture contains now a given number of hidden layers and nodes, but it would also contain models for these activation functions. And as I said, one of the requirements, as you will also see a little bit later when we're going to derive the backpropagation algorithm, is that these functions have easy expressions for the derivatives. We can use it as a kind of a threshold value function. And we also want the derivatives to be continuous. And you will see that when we are setting up the final algorithm for backpropagation here. So one of the more popular ones is something which is called the rectified linear unit. Oops, sorry. And this is shortened to just ReLO. And there are many variants of that. There's an exponential linear unit. There is a modified, rectified linear unit, etc., etc., etc. So what we are going to do now, in our case, this variable c, which we put up, and now we write it as a vector. This is the input to the different hidden nodes, is going to be given by this matrix W multiplied with x plus this vector b, as we wrote it here. So this is the vector which contains the biases, and the output h is now given by this function sigma of wx plus b, and the function which we have, this rectified linear unit, looks something like this. If as a function of z, so we have a sigma of z here. So this is the same as our sigma of z. it is 0 up to z is equal to 0. And then it's simply a constant. This is going to create problems when the argument is less than 0. There are cases where we will never have arguments less than 0, and then this function is okay, but we have to be a little bit careful with the kind of functions which we have. So this function sigma z is now given by a very simple mathematical function, max of 0 and the input argument z here. Now this function has also a very simple derivative, as you will see, and then we are going to set up these different activation functions. We are going to make a list of them, but let me just set up so the derivative here is actually just a constant. So if we have so in this specific case, sigma z is equal to 1 for z larger than 0. Now we have other such functions which are very popular, and let's just set them up here. So other activation functions, and these define now the model which we are setting up when we are setting up the architecture for a neural network. So think of these as model parameters. In the same way as we previously in linear regression, we were setting up a model for a polynomial of a given degree. So we have other activation functions which are very popular. So let's just list them. So there's something which you have seen, most likely you have seen. So one of these is the sigmoid function. And this sigma z is now given by 1 over 1 plus e to the minus z. And this is a function which has been very popular in neural network applications. It has actually a problem, however. It leads to what is called exploding gradients. And you can see that, or vanishing gradients. In particular, the problem of vanishing gradients has been one of the problems with the sigmoid function. Its derivative is simply given by sigma z with the above expression of 1 minus sigma z. Now, if you make a plot of this function as a function of z, so this is the sigmoid function, what you will typically see then is that the function can take values like this. So this is very schematic. When the values of z become very large, then the function becomes basically flat. That means that when you look at values for the derivative in this region here, then sigma, the derivative, is getting close to 0. And this is going to give problems when we are going to train a neural network. And I'm going to just write it here, and we are going to see that a little bit later. So with so-called vanishing gradients, because the gradients, when we have set up the expression for the backpropagation algorithm, the gradients are going to be proportional to the derivative of the activation function. And you can see now that this function here becomes very flat when c becomes large, absolute value. And then we can run into problems with derivatives which vanish. Now we have another very popular function, which is the tan h, which has a shape which is similar to the sigmoid function. So the sigmoid function is a kind of, you can easily interpret that as a kind of threshold function, because you will say now that if the value is smaller than a specific value here, then you put it to 0. And if it's larger, you put it to 1. The tan h has a similar behavior. So the tan h function, just to remind you of that one, would be a tan h with argument z. And then its derivative is now given by 1 minus tan h of z. And this is squared. And in this particular case, z lives in -1 to 1. So depending on the situation which you have and the type of variables which you end up with. So in this case, for the sigmoid function, it goes from -infinity to +infinity. Another very popular one is the ELU function. So these become parts of your model. And this sounds a little bit frustrating, but at the end, when you're training a neural network, you would actually play around with different activation functions. And you would then pick the activation function which does the best job for your data set. There's something which is called the exponential linear units. And in this case, we have a sigma c, which is equal to a parameter alpha. And this becomes a parameter which we have to set, becomes a hyperparameter. And we have a plus z minus 1. And this is in case z is less than 0. And then we have just z in the case when z is larger or equal than 0. No, sorry, this is larger than 0. And this is less than equal than 0. There's another one. So if you look up in the literature, you will see many such activation functions. And one is called the leaky ReLO, which is a modification of the ReLO function which we saw before. And this is also widely used. So that has a parameter alpha times z when z is less than 0. And we have equals z when z is larger than 0. So in this specific case, the derivative is also, and that applies also to the exponential linear rectified linear unit. In this case, the derivative is just equal to alpha. And alpha is typically set to a small parameter. So this could typically be 10 to the minus 2, just to give you an example. And it's given by alpha when z is less than equal than 0. And it's equal to 1 when z is larger than 0. So these are the type of some of the more popular activation functions. You could even take the step function if you want to. But let's now just look at this, the leaky ReLO function here, this specific function. And let's try to go back to the XOR gate and see if we can make some calculations here. So let's go back to the XOR gate. So we are going to, what I'm giving you now is the result of a training, okay? So the parameters which you have are what have been obtained through the training with a neural network. So from training, of a neural network, and this is the thing which we are going to build gradually here. But now I just wanted to show you some possible parameters for a neural network here. So what I'm going to have is a matrix W. This is the first matrix for the hidden layer with 1, 1, 1. And then I'm going to have the bias for the hidden layer, which is now just going to be given by 0 and minus 1. And then I'm going to have the weights. So for the output layer, so these are the weights from hidden to output layer. And if you now look at the network which we put up, so what we have, the model which we have set. So this is our model. So we have 2 weights and 1 bias from the hidden layer to the output layer. We have 4 weights and 2 biases from the input layer to the hidden layer. And we are going to use this rectified linear unit. So the activation function which we are going to implement here is actually this activation function. So it's pretty easy to set up. So when we look at that one, so these are actually the results I obtained from a training. This W is going to be given by a vector with 1 and -2, and the bias for the hidden layer, the output layer, is actually equal to 0. Now, our design matrix X does not now include any intercept. It includes only the data X. So that means that the data X has simply to be given by 0, 0. It's a 0 and 1. It's a 1, 0, and 1, 1. So we actually have to be a little bit careful here with the way we are setting up the data. Now, this is something I want to come back to. And it's a kind of philosophical, not exactly philosophical question, but it's more a question of how we are going to set up a neural network and how we are going to treat the input. Now, if you think back to what we did with a polynomial representation. So what you could do now is to let your design matrix represent a polynomial to a specific degree. Okay? And then I could train my neural network to reproduce a polynomial with a given degree, assuming that that polynomial. So what I'm doing now is to mimic what we did with linear regression. So I could set up a design matrix which goes beyond the just the input values. So I hope you're following me now, because it's a kind of it's an important thing to think of when we are training a neural network. So I could train a neural network if I want to fit a function with a polynomial by just feeding in a polynomial to a given degree. So that would already be a model. And then I would let my neural network, which is a model, to find the best representation of that polynomial. That may, however, not be equal to the data which we want to reproduce. So a neural network, what it is doing, it is trying to fit with a given error and a given number of hidden layers, a given function. Now, the alternative to you providing, let's say, providing a design matrix with a given polynomial degree, if that is what you're doing, is actually to just feed in the data as they are. So if you think of project number 1 and this specific Franke function, which is just this kind of vanilla function we cooked up, then you would just feed in the X and the Y values, and you would let the neural network find the best function approximation to your data. So you have different philosophy. You can feed in an already existing model, which could be this polynomial, but then you would force the network to reproduce data given by a specific polynomial, which is already a kind of model. So the flexibility of a neural network is much, much stronger than this. And the thing which is nice then is that you can just feed in the data and you can let the network, through the optimization, find the optimal representation of the output data which you're looking at. So here now, if you remember back to when I did the linear regression case, if we just go back a little bit to what we did before the break. So what I did then was to have a design matrix, which then contained the intercept. In that sense, what I'm giving in as a model here is actually already something which has been defined by this simple linear regression model, where we assume a linear dependence of the unknown parameters, the W and B. Now, what I'm doing here, on the other hand, is I'm simply taking the values of X1 and X2, and I'm feeding them into my neural network. So we know that this is a matrix, which is a 4x2 matrix. Sorry. So this is a 4x2 matrix. And then we have that our matrix W is a 2x2 matrix. So we actually need to be a little bit careful when we're doing the operation. So we actually need to do X times W. And if I run that calculation, that gives me a 2 by 2 matrix. And then if I add the bias vector to that, plus this bias vector B, then what I get is a new matrix, which is now going to give by 0, -1, 1, 0, 1, 0. And then I have, and I think this should be a 2 and 1. Then I'm going to use the activation function, this ReLU function. And when I do that, so which would be sigma times x w plus b, when I do that, I'm going to get an output which looks like 0. This is the output from the hidden layer, 1, 0, 1, 0, and 2, 1. So now I'm just using the ReLU function and take this z as argument. And the arguments are given by these numbers, which you see in the columns here. And then if I multiply this with the weights, my next step now is to simply multiply with the weights for the output layer. What I'm getting then is an output. And if I use this activation, the same activation function, I get an output which is 0, 1, 1, 0. And that's exactly what I want. And that's equal to the target, which is equal to 0, 1, 1, 0. So a neural network like this one with a hidden layer is able to reproduce the case of an XOR gate, which is actually a non-linear case if we are thinking of separating things into just a plane here. And the thing which we're going to look at now is the setup of a general neural network. And this is going to lead us to the derivation of the backpropagation algorithm. So a general feed-forward neural network and the basic algorithm and basic algorithm. So what we are going to have is a feed-forward stage with a given architecture, with a given number of hidden layers, given, let me just rewrite that one. My handwriting was not optimal here. With a given number of hidden layers and nodes, and activation functions. And I just write this as a sigma of z with randomly initialized weights and biases. And we are coming back to what kind of random initializations we're going to deal with. Then this feed-forward stage, this produces an output. When we just reach the output layer, produces an output which we would feed in to the cost function into a cost function and compare with targets. And compare with the targets, which are our data we want to compare with. And we label these as T. Then This feed-forward stage is a stage now where we have not done any training on the weights and the biases. We just initialize them randomly. So the next step is what is called the back propagation step. And in this back propagation stage, what we actually do then, and this is the same as reverse mode in automatic differentiation. And we are going to discuss that in more detail next week. In automatic differentiation. So this back propagation stage has the following. So it gives an algorithm, and this is the back propagation algorithm. So back prop algorithm. Algo to calculate gradients of the weights and the biases. So the back propagation algorithm is an algorithm to obtain the expressions for the gradients. Now, when you have that, then you would use any of the gradient descent methods to train gradients, the weights and biases. Use gradient descent, and this can be a stochastic gradient descent with batches and different number of epochs, etc., etc. So use gradient descent to train weights and biases. So I'm going to put numbers here, and I'm going to put this as a number 2, and then number 1. So the next step is to repeat. So this is stage 3. Repeat 1 and 2. So when you now have the new weights and the biases, then you do a new feed-forward stage. So when we have been training, we will typically train and go back to the first hidden layer. Then we have obtained new weights and biases because we started with a guess. With the new weights and biases, we will then go back to the first stage. We perform a new feed-forward, and we produce a new output. So we produce a new output, which then we compare to the cost function. And clearly our convergence criterion now depends on the way we want to approximate this cost function. So if you're looking at the mean squared error, we would like to minimize the mean squared error. So we produce a new output. We compare that with the target values. We look at, for instance, the score, which is the mean squared error. And if that reduces, if that gets reduced, we would continue this process till it reaches a specific optimal value, which we can accept as a mean squared error. So you would actually do this feed forward and back propagation stage, back and forth again, till your cost function has reached a value which you can accept. You will set up a number of so-called iterations. So every time you do the back propagation and the feed forward propagation would just be considered as one iteration. And then we go back and forth and repeat 1 and 2 till the score function, which could be the mean squared error, till score is acceptable. And acceptable means that you have to define what is acceptable or not. So if suppose the mean squared error is 10 to the minus 3, and you're happy with that, then you're done. So this is essentially the basic the structure of a neural network. And the back propagation is the central algorithm for finding the gradients or the derivatives of the weights and the biases. So what we need to do now is actually to set up the backpropagation algorithm. But before we do that, let's now look at let us now introduce the general structure of a neural network. So the backpropagation algorithm, which is the same as reverse mode, propagation, same as reverse mode in automatic differentiation. So let's set this up. And in order to do that, we need now to define some specific variables. So we are going now to have our input layer. And that will contain a given number of input nodes or neurons. So we would have an x1, x2, and all the way down to some xn. Now, if you're looking, for instance, at you classifying an image, whether this is, for instance, a handwritten number, a given handwritten number between 0 and 9, whether it's a cat or dog and so on, in that case, the input would be the pixels which represent the image. So if you have an image with a high resolution, you may have 200 times 200 pixels, which gives you 40,000 input variables. So in case of a high resolution image, you could have a huge number of input nodes. Then I'm just going to write this in a schematic way. This feeds in to a hidden layer. And I'm going to use a variable L to indicate a hidden layer. So we would have a set of hidden layers. And clearly, the more hidden layers you have, the deeper the network. So we would typically use the name deep learning when we are making our network deeper and deeper and deeper. So we have a number of hidden layers. And we obviously have hidden nodes here, which are then all connected with the previous nodes. That leads to mathematically an operation where we multiply a matrix with a vector or matrix with a matrix. And these are so-called affine transformations. So we are not going to do any reduction of the dimensionality here. We have a fully connected, full connection between the different layers. So we call this typically a fully connected neural network. Now, there is no connection between the nodes in a given layer. That would often give a much more difficult training. So some people can reduce the dimensionality of the system by randomly choosing a given set of the hidden nodes. So suppose you set up a hidden layer with 100 hidden nodes. You could choose randomly each time you do the training, only 50 of these to reduce the dimensionality. Now, this continues, and then we reach a layer L. So this is just a plain layer L. And in here, down here, there is going to be a node, which I'm going to call for node J in that specific hidden layer. And this receives input from all the previous ones. So all nodes are connected and produce an input to that specific layer. Now, this continues all the way till the output layer. So this output layer could just have one node, like in the case of the XOR gate, where we just had one data which we predicted, whether 1 or 0. And in that case, we just had 1. If we are looking at the classification problem with 10 handwritten numbers, you would have 10 output nodes. So this is the output layer. And this feeds into the cost function. So this produces your Y, and that feeds into the cost function, which then receives the target values as well, which are then compared with what your model has produced. So what you have to do now is to think of the neural network as a model. So if I now just move down here, I'm going to define the following quantity. So this set J of a layer L. So this is the input value to that layer. This is now given by a sum over I equal 1 up to n L minus 1. That's the number of nodes we had in the previous layer. And this is now multiplied with the weights which we have. And we are indicating this by the weights matrix for the hidden layer L. And this is then multiplied with the output from the given node in the previous layer, plus this bias quantity BJL. So this is this quantity which you see here is the output from node I in layer L minus 1. So if this is the first layer, this A would simply be the input nodes, which would be the excess. Now we call these hidden layers because this is something which at the end you never see. So the only thing which you see when you're setting up the model is the input layers and the output. These are the things we care about. And what happens in between, you can think of that as complicated mathematical operations which try to find the best possible representation of your parameters. So this is one of the variables which we have. The quantity Wij is what we call the weight, or just the weights for layer L, connecting with the previous layer, connecting with layer L minus 1. What we need to set up as well is now the output from this specific node. If I now define this AJL, this is the output from node J in layer L. And we are going to write this AJ of L in terms of a sigma of L. We can have different activation functions for the different layers of set GL. Then what we can continue with is to define a cost function. And this cost function is a function which then depends on a typical problem which we have. So the example which I'm going to look at now when I derive the backpropagation algorithm is just a mean squared error. And this mean squared error will now depend on the parameters which we have, these parameters theta, which are given by all the weights and all the biases. And in our case, this can be given by 1/2. I'm skipping the 1 over n, which we have seen previously. We sum over all the values which we have. So we have the outputs, y of I, minus the targets, t of I, and this is squared. And then we also need to define a typical activation function. And in the example which I'm going to run through first, I'm going to set up the sigmoid function. So typical activation function is now going to be given by my sigmoid. So I'm going to have an AJ of L, which is now given by this specific activation function in that layer. And in our case, this is just going to be the sigmoid function in the example which now follows of minus Cj of L. So these are the preliminaries which we now need in order to set up the backpropagation algorithm. So we have defined the different inputs to a given layer. We have defined the weights and the biases which need to be defined. And then we have a cost function and we have a typical activation function. So next week, we are going to start from here and we are then going to derive the backpropagation algorithm. And we are going to link that with the reverse mode in automatic differentiation. And that will also show you why it's so useful to think of using automatic differentiation when we are setting up neural networks. Now, this is going to conclude today's lecture, so I'm going to stop the recording.